Welcome to example 1, where we're trying to determine the torque of two different scenarios, A and B, and then I'll do C and D in a different video. So imagine you're like an amateur plumber and you're unable to loosen some pipe fitting. And so what you decide to do is you slip a scrap piece of pipe on the end of the wrench and effectively make the torque larger so that you can basically get the pipe loosened. So this amateur plumber basically applies his full weight downwards of 900 newtons, and by standing on it, he's able to loosen this nut. And so we're just simply asked to find the magnitude and the direction of the torque about this pivot point right here, the center of the pipe fitting. Now, you might want to stop the video and try it on your own, and then see if you get the same answer as I will do. And plus, there's several methods of solving it. Okay, so assuming that you have already tried it on your own, let's just go with that general approach. Torque is equal to R, which is the position vector, multiplied by F, which is the force vector, multiplied by the sine of the angle. Okay, so your position vector R is right there. So it's that distance from the point of rotation to where the force acts. So that is 0.8 meters. The force is 900 newtons. And the angle, I'm wondering how many of you guys wrote sine of 19 degrees. That does not get you the right answer. This is wrong. You see, the angle in our torque formula is the angle that is between the force vector and this position vector. Imagine if you're going to extend this out all the way out this way. The angle is either over here, which is 71 degrees. Remember, if you extend this down here, this is 90 degrees because it's straight down perpendicular to the ground. And this one would be 109 degrees. It's not 19. The angle between this position vector and the force vector is either 71 or 109. Either one of them will work. If you choose sine of 71 degrees, you're going to get a torque of 680 Newton meters. If you choose an angle of 109 degrees, you're also going to get the same answer. You remember, maybe from your math classes, you remember that the sine of 180 minus the angle theta is the same thing as the sine of the angle. All right? So this is the magnitude of the torque, and then we also should state the direction of that torque. And that force would produce a counterclockwise, so it's going like this. This is a counterclockwise torque. So you can write this as in square brackets as CCW, and I can clearly see the direction and the magnitude of that torque. Or if you're just using our sine convention, you can simply write 680 Newton meters. It's really just positive. It would not be negative, because a negative would imply that it would be a clockwise torque. Now, there are actually two other methods that you can apply. Let's talk about them so that maybe you did try that. Just as intriguing to see other ways of doing this problem. This is the general approach that most people would take. You could find the torque by using the force, the magnitude of the force, multiplied by what we call the moment arm, or the perpendicular distance to the force line of action. Let me show you what that looks like. So this dashed blue line is the line of action for that force vector. And this distance here, this is what we call the moment arm. That's our perpendicular. You can get this distance through a variety of ways. You know the hypotenuse of this right triangle. And you know this angle 71 or this angle 19. It really doesn't matter to me. You could use the sine of 71 degrees is equal to r perpendicular all over 0.8 meters. So r perpendicular would be 0.8 multiplied by sine of 71, which would give you 0.76 meters. So now substituting in here, we have a force of 900 newtons multiplied by our perpendicular distance called the moment arm of 0.76 meters. And this will give you a torque of 680 newton meters. And it would be positive because it would be counterclockwise. Alternatively, you could use the perpendicular component of the force. So the torque can be calculated by using the perpendicular component of that force multiplied by the position vector r. And the perpendicular force would be the component of this force that is perpendicular to this position vector. There's that perpendicular component of that force vector, and you can solve for that by making a little triangle with this. This angle right in here would be 19 degrees, and so the cosine of 19 degrees, for example, would be equal to F perpendicular divided by the hypotenuse, which would be the 900 Newton force. So F perpendicular would be equal to 900 times the cosine of 19 degrees, which is 850 newtons. So then 850 newtons of force is actually making this pipe twist around here, multiplied by our position vector of 0.8 meters, and this will also give you the same torque that you had earlier of 680 newton meters in the counterclockwise direction. And I'll just go ahead and put back the same solution we had earlier. It really doesn't matter how you solve it. So go ahead and now do part B here and solve for these two individual torques. Okay, assuming that you have done it, you would simply, I'm just going to use just general formula. R times F times the sine of the angle, then substitute in our data. And substituting, we'll get a torque of 3.76 Newton meters, and this is going to cause it to go counterclockwise, which you could just simply write as positive 3.76 Newton meters. By the way, you could also use, instead of an angle of 70 degrees, you could use an angle of 110 degrees between the force vector here and the arm vector, and that will also give you the same result. Okay, going on to the second version, applying the same formula, and then substituting, you get a torque of 3.93 Newton meters going in the clockwise direction. And a clockwise torque is a negative torque based on our sign convention. Okay, that's it for example 1A and B, and the next video I'll do examples 1C and D.